Good. All right. Hi, everyone, and welcome to this training on using Python and Jupyter Notebooks on Savio. My name is James Duncan. I'm a domain consultant with Berkeley Research Computing and a PhD student in biostatistics. And I'll be presenting the material today with Chris Pachorik, who's a professor in statistics and also a domain consultant. And we're both a part of the Berkeley Research Computing program within Research IT. And we partner with faculty, students, and staff to help with their data and computation needs in order to advance research on the UC Berkeley campus. So we'll start off with a few announcements. Research IT is hiring several graduate student domain consultants, the same position that I have, for flexible 10 to 25% appointments. So if you're interested, you can email your cover letter and CV to this email address. And I think this is a really great way to learn more about research data and research computing. And I've really enjoyed it. Our next cloud computing meetup is on Thursday, December 9th at 1 p.m. It's going to be focused on startups using cloud technologies. And these are a regular meetup that brings together both researchers and staff that are interested in cloud computing. We're also looking for researchers that are currently working with sensitive data to help build out our tools in this area. So if you have sensitive data or plan to have sensitive data in the future, reach out to us and let us know. And finally, just a reminder that if you ever have compute questions, you can visit, and I should say, or data questions as well, you should visit our weekly office hours. Our Wednesdays from 1:30 to 3 p.m. and Thursdays from 9:30 to 11 a.m. And you can find the Zoom link at this URL. So a quick outline of the talk today. We'll talk about using Python on the cluster and Python package management. And then I'll go into both an overview and the pros and cons of different package managers, such as pip and Conda, and also best practices when using Conda environments. Then we'll go into talking about Jupyter Notebooks via OnDemand on Savio, as well as monitoring, debugging OnDemand jobs, and also creating your own Jupyter kernels from a Conda environment. And then we'll talk about ways that you can modify a kernel that you've created to use software that's already available on Savio. And we'll end with an overview of basic parallelization strategies in Python using IPyParallel, Dask, and Ray, and a little bit about parallel processing within the Jupyter Notebook environment. So we'll do most of this today as a demonstration with lots of code examples. So I do encourage you to log on to Savio if you already have an account or in your local environment and try out some of these various examples for yourself as we go through them. A lot of this material is based on our documentation, so please check that out. And these materials are available at this short URL, which leads to this GitHub repo. And you can also just download things as a zip file. So feel free to follow along.
Hey, James,
Okay.
do you want to say something about taking questions and that there are various of us here who can answer questions in chat?
Yeah, good point. So there's a lot of experts that have a lot of experience with Python and Jupyter and OnDemand. So feel free to ask any questions you have in the chat, and hopefully they'll be able to answer that. We also plan to leave hopefully about 10 minutes at the end for additional questions. So yeah, either way, whatever you prefer. Okay, so first step when you want to use Python on Savio is, like many different software that's available, you would access Python via the module system. So in this case, module load Python will just load the latest version that's available, which is 3.7 on the system. Or if you need a specific version, you can module load Python / and then the version number. To see what versions are actually available, you use this command module avail. And right now we have Python 2.7, Python 3.5, 3.6, and 3.7, as well as some versions that were installed by the consultants like me. We plan, I think, next year to add Python 3.9, so keep your eyes out for that. Don't forget to load in Python because there actually is a sort of system provided version outside of the module system, which lives at user bin Python. That version is 2.75, and you won't have access to pip or conda that we'll be talking about. And we strongly caution against using Python 2 at all. It's no longer supported by the Python Software Foundation, so it's really reached end of its lifetime. So after you've loaded in Python, you can now run Conda commands, and we'll talk more about exactly what Conda can do. But a quick way to see what Python packages are available by default on the system is to run a Conda list, and here I've just piped that into head to limit the output. And you can see, for example, we have this package Alabaster and tells me the version number. And since I've module loaded Python 3.7, which is the default Python, it also tells me that build. It's also telling me here where these packages are located on the system in this read-only directory. So we have many common packages that you might be familiar with, including packages for scientific computing like NumPy and SciPy, package for visualization, packages for parallel computing, packages for data ingestion and manipulation, packages for data science, and many more. So take a look at this list, and you may find that you already have everything you need to get going with your jobs without having to install anything additional. There's also some other machine learning packages that are available via the module system. So I've typed here module avail ML, and this shows me all these different packages that are prefixed with ML, including MXNet and TensorFlow. And we also have a consultant version of PyTorch that you can find, somewhat older version for Python 3.6. And a lot of times these are installed this way because they might require some additional libraries like CUDA that when you load in this module, it's also loading those libraries in at the same time. And here you'll see the Python version appended to the end of the module name. So this module will also load in the appropriate version of Python at the same time, so you don't have to do a two-step process. But if what we have by default isn't sufficient for your jobs, then you'll probably want to install your own additional packages on this system. So this first strategy I'm going to talk about is called pip. Pip stands for the package installer for Python. And you can use it to install packages in a variety of ways. First of all, and probably the most common way, is from the Python package index. And to do so, you just run pip install. You need to include on Savio this -- user flag, which tells pip to install this into a user directory in your home directory called .local. In this case, I'm installing scikit-learn. Scikit-learn is already available on the system, so I need to include -- upgrade to install a newer version than what's currently there. Another strategy is to use version control. So by writing git plus and then a URL to GitHub, GitLab, Bitbucket, or some other Git version control online repository, I can download a package directly from GitHub and install it in my local environment. You can also install from local project directories. This might be useful if you're, for example, doing some development work or you've got a package that you're writing and you want to use on Savio. You might want to install that directly from the source code. And to do so, you use this -e flag, which stands for editable. And if you're familiar at all with package development in Python and setup tools, then this is very similar to doing Python setup.pydevelop. If you're not familiar with that, don't worry about it. And then a final way is to install from some sort of archive file, possibly compressed. Um, this last method that I'm showing here using -r, which stands for requirements, is to install a number of packages all at once from a file that contains one line for each package that you want to install. So this is, often a helpful way to share your particular environment with other users if you're using pip. Just a warning, if you are using the default version of pip that's available when you module load Python, that conda list command that I showed at the beginning won't actually show the packages that are installed via pip after module load Python. So use pip list -- user to see what you've installed into your home directory. So yeah, as I said, pip will install into a user directory if you use -- user, and specifically it goes to .local/lib/python and then the version number and then site packages. So in this case, I'm assuming that you've module loaded Python 3.7. So here's an example. I install scikit-learn, and then when I go and list that directory, I see that scikit-learn is available there, as well as some other packages that were installed as dependencies of scikit-learn. So you can imagine, you have a 10 gigabyte limit to your home directory, so you can imagine that quickly you might run out of room if you're installing quite a few packages. So one strategy we recommend to mitigate that is to just move this .local directory to your Scratch. And then you can create a symlink within your home directory, basically a pointer that says, anytime you're trying to access a file at home directory.local, go and look in the Scratch. And that way packages are installed onto the Scratch file system rather than taking up your home directory space. An alternative here that you should be aware of is to use an environmental variable to tell pip where to install packages locally, called Python user base. And then that'll change where those packages are installed, as well as where Python, when you're running Python, will go and look for packages. So this can be set per session if you just want it temporarily, or more permanently within your bashrc file. When it comes to uninstalling packages with pip, it's simply just pip uninstall, and then a single package or a number of packages. And if you want to uninstall all the packages that you've installed in your home directory, you can use this trick to run a command called pip freeze. Pip freeze is helpful for reproducibility, as we'll see, because it'll output a whole list of packages and the version numbers that you have installed and access to. Of course, adding -- user only shows the packages that are installed locally. And then you can pipe that into xargs, and what xargs is doing is taking each line of that file, passing it to pip uninstall, and with -y just meaning that, yes, you should run the uninstall without any further user input. If, on the other hand, maybe you want to uninstall specific packages, you could first filter out that list, or do something like write that to a file and then only, include the packages that you want to uninstall at a certain moment. Unfortunately, pip uninstall doesn't remove any package dependencies. So you can end up having a lot of packages still in your local environment, even after you've done a lot of uninstalling, that you don't need any longer. Pip auto remove is a Python package that may help with that problem, but I personally have not tried it myself. So if you do plan on using pip, definitely take a look at the documentation. There's a whole lot more to learn than what I've been able to cover here. Okay, so let's switch gears and talk about Conda. So Conda is also a package manager like pip, but unlike pip, it's also an environment manager. So environment you can think of as a way to isolate your set of packages for a particular project. To create an environment, you can use the conda create command, including a name for the environment. So in this case, I'm creating a completely empty environment called my_env. And this will create a directory in your home directory called .conda. And within that, there's a directory called envs, and that's where you'll find the my_env directory. To activate the environment, you would run source activate my_env, and you'll see that at that point, my command line prompt has been prepended with this my_env, and I can proceed by installing the packages I need and running my computations with that environment activated. And then when I'm done, I can source deactivate. So oftentimes you might want to create an environment, source activate the environment within your within your SBatch script, and then all of the software that you've installed in that environment will be available during the job. You'll see when you run source deactivate, I get this deprecation warning. So just a quick note about that, so you might have seen, if you've used Conda before, that you'll typically run Conda activate rather than source activate. But this also requires you to run Conda init first, which we actually don't recommend on Savio because it can modify your bash.rc file in ways that have detrimental effects to your shell more generally. Anecdotally, I think that some users have been able to get this working just fine on Savio. So if you do choose to try to use Conda init, just also be sure to set auto activate base to false, and that'll prevent Conda from trying to activate the base environment, which exists in a read-only path on the system. Okay, so when it comes to installing packages, Conda is a bit more restrictive than pip, and there are two main ways. So the first is to install from various Conda channels that are available, such as the default channel, which is what you'll use if you don't include any channel in your Conda install command. Conda Forge, which is a very commonly used channel, and BioConda, which has like a lot of bioinformatics software. So in this first example, I Conda install SciPy, and I'm just using the default channel because I haven't made any modifications to my configuration for Conda. You can use -c to specify a particular channel to install from. So here I'm going to install SamTools, which is not available in the default channel, but is available here in BioConda. And in this case, I'm saying go ahead and update SciPy using the channel Conda Forge. A more advanced method is to install from an archive file, but actually doing so won't resolve any of the package dependencies. So this in general is not recommended, but may in some cases be useful. And just a warning to be sure to activate your Conda environment before trying to use Conda install, because otherwise Conda will try to install into the system environment and you'll get an error. Okay, so you can customize Conda's configuration using the conda config command. So for example, one common thing you might want to do is to add a particular channel with high priority to always use by all your environments. And you could do that using this command. So conda config --add channels conda forge. And what this does is adds conda forge to the very top of the channel list. So it's going to look there first for a package before then falling back to the default channel. If you wanted to put it at the bottom of the priority list, you would use --append instead. And here's an example where you actually do this not for all environments, but for a specific environment by adding the --env flag to conda config. And now these three methods, so the first two methods will modify a file called .conda_rc in your home directory. And that's how Conda is applying that configuration to all environments that you create. while the third will create an environment-specific file in that environment directory. Quick note about using pip within a Conda environment, and I'll start with a warning because this can create issues because Conda doesn't consider pip installed packages when it's installing additional packages. So you want to be careful when combining Conda and pip. And you can sort of help to ensure that things don't go badly by following these best practices. So the first is to use pip only after you've done all your Conda commands. So you've gone through, installed all the packages you want via Conda, and then at the very end, you'll install a package, maybe that's only available on PyPy. If you find that Conda changes are needed after using pip, then we recommend creating an entirely new environment where you install all the packages, including the new packages that you need via Conda, and then redo what you did with pip. And there's a way that I'll show in a moment that you can do that fairly easily. Also, within a Conda environment, when using the version of pip that's installed in that environment, you do not want to use the -- user flag because that would install the package into your home directory just as usual. Instead, you want to just call pip install directly, and that'll install the package within the Conda environment. And then finally, always run pip with upgrade strategy only if needed, which is the default. So as long as you aren't tempted to change this, you don't have to worry about it. There's also an experimental option, config option called pip interop enabled, which tries to take into account the package versions that pip has installed when Conda is doing its dependency resolving, which I'll talk a bit more about. So that's experimental, and I haven't tried it, so I'm not sure how well that works, but it can, I think, slow things down a bit when you're installing packages. Okay, so we saw already an example of upgrading a package. So say, here's an example of just updating SAM tools. So within an environment, you can get newer versions of package. But let's just say some change that you made could be an update, or just installing a new package results in errors. Formerly, code that was working is now no longer working. Well, you can actually roll back these changes using Conda by running conda list -- revisions. And this will be aware of all the changes that Conda has made to an environment. And you can identify the number for a revision when your code was last working. And by running conda install with -- revision and the number that was previously working, you'll be able to get back to a state in your environment that before the errors began. And again, another reason to be sure to use pip at the very end is that Conda won't show any revisions for changes made by pip. So they actually can't be rolled back in this way. You, like pip, can change installation directories in a couple different ways. So yeah, when an environment is active, packages will install in that environment's directory. You can also install packages without having an environment active just by using the -- name flag with conda install. And you can also create environments and have them exist at a specific path of your choosing. So for example, here I've just decided to, in my Scratch directory, create a conda directory and have my environments in there. But when you do this, you'll then have to source activate with the full path to the environment rather than just the environment name, as you were able to before. And yeah, like .local, you might also consider moving .conda to Scratch and then creating a symlink. In terms of removing packages, there's the conda remove command, which you can specify with an environment name or just directly within an environment. In order to remove an entire environment, which amounts to removing all the packages, associated with that environment, you would run the conda remove command additionally with dash dash all. And then conda clean helps remove unused packages and tarballs. So when conda installs a package, you'll find that there's in the .conda directory, there's a folder called pkgs packages. And conda will try to find an existing cached version of the package in that packages folder, and then just create some links from your environments so that it knows where to find those packages rather than downloading the package again and installing it again. But when you remove packages or remove environments, sometimes you may find that packages you no longer need end up getting left over in that packages folder. So conda clean is a good way to just get rid of anything that's not currently being used by an environment. And this dash dash dry run here will just tell you exactly what the command's going to do if you want to see what will happen without actually making any changes. Okay, so I'll just summarize some pros and cons of these two strategies. So with pip, you can use system packages that are already there. New package versions often come out on PyPy first. So if you want the latest and greatest, a lot of times pip will be a better choice. Pip has a larger number of packages for all sorts of things because pretty much anybody can upload a package to PyPy. It also has some more flexible package installation methods. It tends to be a bit faster than Conda because it's not doing what Conda does to simultaneously check compatibility for all dependencies that a package and its co-packages in the same environment need. With pip alone, you are limited to the Python versions that are already available on the system, so the highest version of 3.7. And there's none of this automated dependency cleanup, although this pip auto remove may help with that. And finally, pip includes only Python packages. Conda, on the other hand, creates self-contained environments and can use any version of Python. It just treats Python as another package, so you can install, the latest version of Python easily. Conda clean helps remove unused packages. If you made a change that didn't go well, you can roll that back pretty simply. They're not just Python packages. There are also compiled libraries that Python packages might need or completely separate from Python. So you can go well beyond Python via Conda. And it tries to ensure that all dependencies are compatible. The downside to that is that it tends to be a bit slower. Environments, since you're a lot of times installing Python, can become quite large on disk, and in some cases even cause I/O issues on the system. And next year we'll be giving a training on I/O best practices on Savio, so definitely look out for that if you're using Conda. And there's also a somewhat more limited number of Python packages available. Okay, in terms of reproducibility, so I mentioned this pip freeze. This will give all packages that are installed in your environment, including local and packages within the module system. And you can output that to a file called requirements.txt, share that with a collaborator, and they should hopefully be able to get an environment that's approximately the same to what you've been running your computations on. With Conda, there's a similar command called conda end export. And this is a YAML format. And this will include not only packages installed via Conda, but also via pip. So one strategy, if you need to recreate an environment, you've decided you need some additional Conda changes after using pip, you can output one of these and then add your additional Conda packages to this list and create a new environment directly from the environment.yaml. Even better in terms of reproducibility and sharing is to use a container. So on Savio, this would be a Singularity container, or maybe a Docker container in other places, and to have just exactly all of the packages as they were when the computations were run for your project. And you can then share that directly, and it should just work for your collaborators. The advantages here are there are some benefits to what these I/O issues that I mentioned. It's very portable, but there is more of a learning curve if you're using containers. So check out our training on containers on Savio. Okay, so switching gears now, I'm going to talk a bit about Open OnDemand, which was recently added to Savio, and it allows users to access various interactive applications with the full Savio infrastructure, including Jupyter Notebooks, which is what we'll talk about today, RStudio, MATLAB, and some, in this case, additional apps like VS Code, which is for code editing. You can find out more about Open OnDemand if you'd like at this URL. So I think I can quickly go through a demo here. So this is when you log in, you'll log in with your usual username and PIN and one-time password, just as when you're SSHing to Savio. And this is the first screen that you'll see. The main thing of importance here that we'll be interacting with is this interactive apps tab. And here you can select MATLAB or the other apps that are available. For now, we'll look at Jupyter Server, and we're going to compute via Slurm using Savio partitions. So this might be a little bit slower right now, given that quite a few people are probably on Open OnDemand for the training. And on this page, you'll be asked to input a number of Slurm flags, so very analogous or similar to what you would be doing when creating your SBatch scripts or creating your interactive jobs on via the command line. So you can select a partition. For example, if I select a GPU partition, you'll see that it's asking me the number and types of GPUs. So this is like the GRES flag if you've ever used GPU nodes. You can select an account if you have more than one for the job, and then a quality of service. So here I'm going to use a Conda that I'm part of, and let me switch back to just Savio 2. And finally, the number of compute nodes, the wall clock time in hours, and you can optionally give an email address if you want to be notified when the job starts. So I've actually already started a job up earlier. So you'll be taken to this page, and typically while the job is waiting to start, it'll say pending. But once the job is ready, you'll have a panel like this. You can click Connect to Jupyter. And this will take me to the Jupyter File Explorer. So here you can see that I'm by default in my home directory. I have access to all the files in my home directory, and I can get to Scratch and other places on the system. And so in this case, I'm keeping some Jupyter notebooks in this folder. And by clicking New and selecting one of these options from the dropdown, I can start up a Jupyter notebook. So in this case, I've just selected Python 3.7. What I was doing there was actually selecting a kernel for this notebook. And a kernel basically provides programming language support within Jupyter notebooks. So this could be Python. By default, it is Python. But it's also possible to use other languages. And so for example, here I've installed a Julia kernel for in my home directory. And I'll talk more about creating your own kernels. But by default on the system, we have the various versions of Python, and we also have some kernels that are set up for TensorFlow. And then I believe this PySpark kernel is there as well. So, at this point, I can start using any valid Python commands, or I can include Markdown to create documentation for my project. Okay, so, and one thing I forgot to mention is just that you also see a session ID. And just so you're aware, there is an an on-demand folder in your home directory, and some logs and scripts that are pertinent to starting up Jupyter sessions will end up here, as well as other open on-demand apps. So these typically aren't super important for your debugging purposes. They're more important for our sysadmin purposes, but just so you're aware of why it's there. Yeah, one thing I also forgot to mention. So you can, if you're more accustomed to using Jupyter Lab, you can just replace everything from tree on in the URL with lab, and that'll open up Jupyter Lab. Yeah. So this is the Jupyter Lab interface, which I find to be a little bit nicer. In this case, I already had a terminal open, luckily, which opened it again for me. And this is a nice way, as you're running computations in a Jupyter notebook, to open up a terminal, and then you can, for example, see what's happening on the compute node that you've been given access to make sure that your jobs are using the resources that you expect. And all jobs that run on Open On Demand will also, they're batch or Slurm jobs, so they'll be part of the system, and you can take a look at what's happening with SQ, or the more traditional SQ-U with your username, and you'll see that I have this job with the name of the job and that it's running and how long I have left and things like that. Okay, so yeah, so in terms of troubleshooting tips, if you're having trouble getting your job started, since the flags are all the same as Slurm, one thing you can do is try to run an analogous interactive job from the command line and make sure that that's working. Yeah, so as I said before, you can see the status of the job. There's also, in some cases, users have reported seeing the authentication window that opens that I wasn't able to show you when you first go to OOD, seeing that continuously opening and you're unable to log in. And a lot of times we found that this is because they have other browser tabs they're using OOD. So you want to go back and close that tab, or just go back to that tab. Also, for the debugging and exploration Jupyter node, the resources are limited to just 1 core and 2 gigabytes of memory. So you may find that the kernel is unexpectedly stopping, and a lot of times that's just because of those resource limitations, so be aware of that. Okay, so I mentioned a bit about Jupyter kernels already. Now, I'll briefly talk about how you can make your own kernel. And one common strategy is just to create an environment and then convert that to an IPy kernel. So in this case, I'm going to create a Conda environment, and I want an environment that I can use within Jupyter that has Python 3.9. So I'm going to go ahead and create that environment, install Python 3.9. And here I'm also installing the IPy kernel package. I activate my environment, and then I can run this command, IPy kernel install user, again, to tell it to install into your home directory. And this will create a new kernel specification that you can then use when you're interacting with your Jupyter notebooks. And so you can actually modify these kernels, whether you've made them manually or you've produced them via this strategy, to use software that we have available already on the system. So in this case, I'm going to go ahead and make a kernel that can use this ML TensorFlow 2.5.0 module. So first I module load ML TensorFlow. This isn't strictly a necessary step, but it will be helpful later. And then I'm going to create this kernel with this name. This outputs a JSON file into my home directory at this path. And all this JSON file is telling Jupyter is to start up a kernel with Python 3.7. So nothing else. So this is, at this point, completely equivalent to the default Python 3.7 kernel that we have on the system. So we'll need to edit this file. We'll add a dictionary called env with some environmental variables. And the environmental variables that we need to add are the same that are going to be modified when we module load the ML TensorFlow module. So one way to figure out exactly what's happening when this module is loaded is to module show ML TensorFlow. And you'll see that there's commands in here like prepend path. They're editing my path environmental variable. And you'll also find that it's loading other modules. So these two are going to be important to look at and see what they're doing to the environment. So for this particular use case, I need to modify the path, LD library path, and Python path. So I can just echo those and then copy paste the output into this env dictionary. So here I've just copy pasted my path variable after module loading ML TensorFlow, and etc. for those other modules. So at that point, I can save that file and I'm ready to launch Jupyter and open up a notebook, and I can switch to the TensorFlow 2.5.0 module. In this case, I was on a GPU node, and I can see that things are working correctly, and I'm able to access the GPU via TensorFlow. Okay, so I will stop there and pass it over to Chris.
Great, thanks, James. I thought there was another slide or two coming, so my mouth is still full with the snack I was just eating. Okay, so let me share my screen here. Okay, so the idea here for my section is to talk through a few strategies that people can use for doing parallelization on with Python. And there's a ton of ways that you can do parallelization in Python, lots and lots of different packages that you can use to get your code running in parallel. And we only have time and expertise to cover some of those. So I'm going to cover two main things, and then time permitting, we're also going to talk about a third. So the first one is using the IPy parallel package, and that will basically allow us to divide up a number of tasks that we need to compute and have them run on separate workers. And so those separate workers are generally going to be separate Python processes, and those separate processes might be all running on one node, or they could potentially be running on multiple nodes that you've requested via using the Slurm scheduler. And then I'll talk a little bit about using Dask, which is a Python package that, among other things, allows you to work with very large data sets that get distributed and run and operated on in parallel across multiple workers. And then, like I said, if we have time, we'll talk a little bit about the Ray package as well. Okay, so one of the basic things that you need to be able to do when you're trying to do things in parallel is make sure you have it clear in your head. How do I start up these additional workers that are going to be doing my computation in parallel? And so One way that will often get done is that you would start the workers outside of Python, but actually as of a recent version of IPyParallel, you can actually start those workers from within Python. So that's quite handy. So we'll go ahead and see this in action. So I'm going to switch over from the slides over just to a terminal session where I have, I've logged into Savio here, and I've got the underlying markdown document that was used to prepare the slides. So I have the same code and the same text that is in the slides here. So I'm going to go ahead and start up an interactive session using srun. So this is an alternative to using sbatch when you want to do something interactively. So you could do this yourself. You wouldn't put in the reservation, which is just was just put in place for this training to make sure that I could get access to the to a couple nodes without having any delay. Okay, so now I'm on I'm on this N02222.savio3 node, and I can now start to do my computations. So I'm going to go back to the document here and just show how we would actually start the workers from within Python. So I'm going to do module list just to see what I have active, and then do module load Python 3.7, similarly to what James did. And then what we can do is we can basically import the IPyParallel package, check that it's the version that will allow us to just start the workers from within Python, and then go ahead and get that all set up. Okay, so we're going to run this command that will say we want to use 4 workers. This would not be particularly effective use of a full Savio 3 node, which will generally have, I think, 32 or 40 cores, and I'm only asking for 4 workers. But you can do this. You're just not going to be using all of the CPUs on the machine. Okay, so we go ahead and run this command that basically starts up the cluster. And we should now, we now have the ability, basically, we started it, we can now basically create this object C, which is basically an object that allows us to interact with our cluster of workers. So we're going to go ahead and do that. And then what this c.ids will do is it should show you the number of workers that you have access to. And so in this case, it says that there's a set of 4 different workers. They're numbered from 0 up through 3. So if you see the number of IDs here that you expect based on the number of workers you asked to start, then you're in good shape to go ahead and then do your computations. I also have some notes here in the slides and that are in this underlying markdown document that if you wanted to start the workers from the shell instead of starting them from within Python, for example, if you were using an older version of IPyParallel, this is the command that you would use from the shell to start the workers. And then once you start up Python, you can then basically connect to those workers with this command here. And then just as I just showed you, you would then run the c.ids and just check that that you had access to the number of workers that you were expecting. Okay, so now we can go ahead and start to basically interact with those workers. And so I'm just going to do a simple test here, and then we'll show actually doing some real work. So I'm going to create this object that gives me access to all of the workers at once, which is why I'm using this bracket and then the colon. This is called the direct view of the workers. And so I'm going to, so now if I just type direct view, it says, okay, this is basically an interface that allows me to interact with those 4 workers. And I'm going to set up the view so that it uses blocking calls. And so that basically means that it's not going to, when I tell the workers to go do something, I'm not going to get control back in my main Python session to be able to do additional things until all of those workers have completed. So in this case, I'm just doing that so it's a little bit more clear when they've finished, and I can sort of know that it's safe to proceed with additional execution. So in this case, I'm just going to run this apply method that will then just run this Lambda function and it will run hello world on each of the 4 workers. Okay, so it looks like I forgot to set the blocking to be true, which is why we got back this thing that's called an asynchronous result, and it didn't actually show me the results. So let's go ahead and make sure that I do the blocking and then run the command. Okay, so now once I've set it up to do the blocking and block things until the execution happens, now I do actually see the result. Okay, so that was basically just a test to see that we can see the workers, we can connect to the workers and do something on each of the workers, in this case, just printing out this string. So the next thing I'm going to do is just walk through what it would look like to do a fairly straightforward, but not totally trivial, not totally silly actual computation. So what I'm going to do is I'm going to take a sort of arbitrary small data set, and I'm going to run a machine learning statistical prediction method on it called random forest regression. And I'm going to do that using leave one out cross-validation. So I'm basically going to take the data set, I'm going to leave out one of the observations. I'm going to then try and make a prediction using I'm going to fit my regression model. I'm going to make a prediction for that observation and compare the predicted value to the actual observation that I've held out. And if I do that once for each of the observations, holding each one out in turn, I can basically assess how well the method does, where I'm being honest about my performance and not basically trying to avoid overfitting or trying to see if I'm overfitting the data. And to get an assessment of how well I'm doing, taking account of the possibility that I'm overfitting. Okay, so in order to do that, I'm going to need to do a little bit of setup where I basically load packages on each. I basically load the Python packages in that I need on each of the workers, and I'm going to need to send some code and send some data to the workers. So that's what I want to illustrate next. So with the direct view, which is this interface that allows me to basically just send commands to all the workers and have them do something, I'm going to load a few packages that I will need for the computation that I'm about to do. So it should be loading these packages on the workers. You can see it's pausing because it's waiting to return the result until it actually returns the result. And it says, okay, I've done. It's now finished doing each of these operations here. Okay, so now what I'm going to do is I'm just going to define a Python function that will do this process of doing the cross-validation for a single observation. So index basically says which is the observation that I'm going to hold out, and y local and x local are the training data that I'm using to fit the regression. So the x's are the predictors and the y's are the observations. So this is a function that will basically just run this random forest regression, and then it will basically make the prediction for the held out observation. So I'm not going to go through sort of the details of what this code is doing, but just to describe conceptually what it's doing. And then for that held out observation, it's going to go ahead and return back the predicted value for that observation, where the prediction was done without having used that observation to fit the model. Okay, so I'm just defining this function locally on the main process here. And then what we're going to need to do is, well, in this case, the other thing I'm going to do is basically just generate some data. So instead of actually reading in data from an actual data set, I'm just going to randomly generate some data just for convenience. So, of course, in your case, you will have generally actually read in a data set from disk, and you'll read that data set in oftentimes into the main process. And now at this point, what I want to do is I want to make the data and this LOO fit function that I just defined above, I want to make them available to each of the workers. So I'm going to create a dictionary that contains those objects, and then I'm going to push that information over to the workers with this dview.push command. So this should set everything up on each of the workers. I think the none basically just means that there's no output coming back to the main process, but it should have sent that information over. Okay, so now I've sort of done all my setup. I've got my packages loaded. I've got my data and my function on each of the workers. I should be able to go ahead and basically in parallel hold out each of the individual observations and do those operations in parallel across the 4 different workers that I have available. Now at this point, I'm going to switch from using this thing that I call the direct view to what's called a load balanced view. And a load balanced view is basically an interface where the IPyParallel package is, and there's sort of a controller object that is basically going to manage which of the workers are operating on which of the tasks. And the basic idea is that this controller process should be able to make sure that as best as possible that all of the workers are busy during the whole course of the computation of operating on all of the different tasks. So in your case, you may have 4 workers and 50 tasks that you need to complete, or 4 workers and 1,000 tasks, or you might have 20 workers and 1,000 tasks. The number of tasks is basically just the number of independent computations that you need to get done. And so I'm going to set up this load balanced view. I'm going to set the blocking again to be true. And now in this case, instead of holding out every single observation, I'm just going to do 50 of them just to keep things simple here. But usually if you were actually doing leave one out cross-validation, you would have as many tasks as you have observations in your data set. And now I'm basically going to just set up a little wrapper function. The wrapper function is needed because when I run the function in parallel using this map operation, I basically need that my function just takes a single input. And then so this function is basically a wrapper that says for index I, which is going to correspond to the held out observation I, I'm going to run that LOO fit function with the ith observation held out and y and x as additional arguments. So the wrapper is just a way to convert something that has 3 arguments to something that is going to just have 1 argument. And so then at one point I was timing the code and I left that in there, but that's not required. So now in order to actually run the computation in parallel across all of the observations, or in this case, across 50, the 50 observations that I decided to hold out, I basically just need to set this up so that I loop over the 0 up through 49, the 50 tasks, and I run this wrapper function. And by calling the map operation on the load balance view, this is basically going to allow IPyParallel to run the 50 different tasks that I need in parallel using the 4 workers, the 4 Python processes that I have. Okay, so then I can go ahead and do this. I'll have to wait for a moment while it actually goes and farms that out to the workers. So we're waiting here because I set up I set things to block so that I don't get results back until all of the tasks are completed. This shouldn't take too long, and there you see we've got our 50 results back. So that's sort of the basic story with IPyParallel. You have a certain number of tasks that you want to run in parallel. You have a certain number of workers that you set up, and then you'll use manipulations like this to basically say that you want to run all of those tasks across the workers. And you'll let this load balance view basically handle dispatching those tasks to the worker so that as a worker completes a task that it's working on, it will then be handed the next task that it should do its computation on. Okay, so let me go back to the slides and just catch us up with where we were. So we've talked about the testing and the example. The other thing that I'll comment on here about IPyParallel is I said before that we could use IPyParallel where we have the workers set up to be running on either a single node of Savio or multiple nodes of Savio. And the slight complication if you want to run on multiple nodes is that, first of all, of course, when you have to basically use Slurm to request multiple nodes, either using sbatch or srun. And then once your job starts and you have those nodes allocated for your computations, then within the shell session that you get either in your sbatch job submission file, or if you're using srun to do things interactively, you'll need to run code that looks like this, that basically says that you want to start up a controller process that's going to manage the workers. And then once that controller process has started up, and that's why there's this sleep command to make sure that it's sort of fully finished starting up, then what you do is you'll run srun IP engine. And what this command does is when this is run within an sbatch or an outside srun session, this will run IP engine once for every one of the tasks that was part of the Slurm's request. And so if you requested, say, 2 nodes and 40 tasks, this would run IP engine 40 times, and that would basically start up 40 of these Python workers. And then there's another sleep command here to make sure that all those workers get to start up. And then at this point, you could go back to what we did basically at the very start, where we had syntax like this, and this would allow me to basically from within Python set up an object that will allow me to interface with those workers, and that's this object C here. So if you're starting the workers externally outside of Python, then you would run this syntax, and that would allow you to connect to the cluster of workers that you started separately. Okay, so the story, so that was IPyParallel. I'll just very briefly say that the story when you're doing things in a Jupyter notebook is very similar. And in fact, because of the fact that we now have this upgraded version of the IPyParallel package, you could basically just start up your Jupyter notebook, and from within the Jupyter notebook, you should be able to just run the commands that I showed a few slides ago to basically start your workers from within the notebook. Previously, with older versions of IPyParallel, there was a sort of an additional step of starting the workers from your Jupyter session browser interface, but that shouldn't be needed anymore. Okay, so the next thing I want to do is talk a little bit about another approach to parallelization, which is involves using the Dask package, which is quite popular amongst Python users. So one thing that Dask can do is it can basically allow you to parallelize independent computations, very similar to what we just did with IPyParallel. So I'm not going to go through exactly how you would do that, but just know that, that's possible. And if you just wanted to use Dask to do that instead of IPyParallel, you can do that. But then another thing that's quite compelling about Dask is it allows you to operate on a very large data set where you can sort of conceptually think of it as a single large data set, but actually behind the scenes, Dask is splitting that data set up into small pieces of the data set and is going to be able to manage the process of running the computation on the data set in parallel, where each of the different pieces of the data set is going to be handled by a separate one of these Python workers or Dask workers. So the nice thing about that is you can increase the speed of processing your data because you're going to use multiple cores to run in parallel over the data. But also the other advantage of this is that if you are running your workers across multiple nodes, then you can potentially, then your computation may speed up because you can basically make use of the memory that is distributed across multiple nodes. And so that can also potentially speed things up because you're now taking advantage of that additional memory by using multiple nodes. Okay, so some of the distributed the kinds of distributed objects that you can use in Dask are there are distributed data frames, and basically this divides up a very large data frame that into smaller pandas data frames. So the Dask data frame is the very large data frame, and behind the scenes, that Dask data frame is just a collection of smaller pandas data frames. You can work with distributed arrays, where basically a very large array is broken up into a smaller set of set of smaller NumPy arrays. And you can use this distributed data structure called a bag, which is basically like a distributed list. And so the distributed list is basically that each chunk, which is being handled by a separate worker process, only contains some of the elements of the list. And so this bag is actually what we're going to illustrate here. So then the other thing to be aware of with Dask is that it has a variety of different ways of starting up parallel workers. And these are called schedulers. So the first one here is the synchronous scheduler, and that's actually not doing anything in parallel. It's just basically there for debugging. Dask can have the different workers be handled by different threads. So these are using software threads, for those of you familiar with that. The different workers can be handled using totally separate Python processes. And then the different workers could be handled in this distributed scheduler as processes running on separate, on separate machines. Now, one of the nice things about the threaded scheduler is that because you're using software threads, those threads can access a given data object without having to make a copy of that object. And so that is one advantage of this first approach. But there are some cases where using threads won't work that have to do with Python's global interpreter lock, and I just leave you to take a look at this note yourself. Okay, so suppose that we were going to use the processes scheduler. We wanted to start up multiple Python processes, one for each worker on a single machine. The way that you would do that is you would start up Python, you would import the Dask multiprocessing package, and then you would basically set this configuration to say that you're going to use the processes scheduler, so that corresponds to this row in the table, and the number of workers that you want to use. And again, if you are operating on one of the partitions on Savio that allocates an entire node or one or more entire nodes to your job, if we just use 4 workers, that's not really going to effectively use all of the cores on the machine, but this is just for illustration here. Okay, so then the sorts of computations we can then do are basically to operate on these on the data set in parallel. And so I have an example here of an example data set of what this might look like. So this is basically, I've got a whole bunch of data that has to do with Wikipedia traffic logs. So this is basically data where the rows so if I go to this location in my Scratch directory, there are a whole bunch of these files, and there are, I think, 192 files. And if I look at any one of these files, I can use gzip to just basically on the fly unzip the file and pass it into head and just look and see what some of the lines look like. basically what these are is for any given Wikipedia page, which is what this fifth column is, although some of these sort of are numbered in a sort of weird way. Or I think the fourth column here. This basically says on this day at this hour for this particular language, so this is a page that's in the Danish version of Wikipedia, how many people visited that particular Wikipedia page, and that's what this number 1 means. And then there's there's another field that shows the number of the size of the Wikipedia page, I believe. So basically what we have is 190 files that contain many, many rows that look like this. And so we might be wanting to do some computation across all of these files where we basically just treat each input row as sort of an arbitrary text string that we want to process on. Now, in this case, the data is more or less in a rectangular format where it's basically just space delimited files. But a Dask bag is basically going to allow you to work arbitrarily with where each row is basically treated as an observation, regardless of what strings or what character strings are contained in the row. So we are running a little low on time, so let me just give you sort of a sense of what sorts of computations you could do. So you would import the Dask bag package, and then in order to, oops, what just happened here?
Okay. I think you went back in the browser.
Yeah, thanks. Let me see where I'm here. Right, great, thanks. So what you would do is you basically say, and it's sort of disappearing off the screen, here we go, is you basically say, what is the collection of files that I want to read into my Dask bag? And so I can use wildcards, for example, to say I want to read in multiple files here, or you could just give it a directory and it will try and read in all of the files. And then what will happen is basically it will assign each of those files to one of the workers, and it will go ahead and read in the data in parallel on these various workers. And the number of partitions in this Dask terminology is basically the number of chunks of the data set that there are. And so then at this point, I can basically then use the Dask interface, the Dask bag interface, to do computations on this entire data set, where I don't have to worry about the details behind the scene of the fact that the overall data set is broken up into these smaller pieces or chards or chunks. So I can do things like with this wiki object, which it represents the overall data set. I could, for example, count the number of lines. And the other thing to know about Dask is that all of the operations are going to be executed in a lazy fashion. So until you basically tell Dask that you actually want to go do some computations, it's just gonna say, okay, I've recorded that you want to do this computation, but it's not actually going to do the computation for you until you do something like calling this compute method, and that will then tell it to go in, and it will then go and read all the data in and do the computations that you ask for, and then return the results back into your main Python process. So I have a variety of examples here of we could basically take the rows and just filter out some of the ones we're interested in and then count them, or there's some examples here of how you could then turn this Dask bag into a Dask data frame by basically treating it as space delimited files. And then you could go ahead and use pandas style processing to basically do compute some summary statistics and things like that. But like I said, we're running a little low on time, but at least I've sort of hopefully given you a sense of what are the sorts of things that you can do with these distributed Dask objects. Okay, so James, did you want me just to sort of briefly go through Ray, or did you want to take it over?
Either way, up to you.
Why don't you go ahead?
Okay. Yeah, and so maybe I'll just go through this as quickly as I can so we have a little time for questions. So Ray is another package for parallel processing that you might be interested in using. It provides a lot of different tools, but the main sort of abstractions within Ray are remote functions, and which they call tasks, and remote classes, which they call actors. So here's how you can, different strategies for installing it. You init Ray, and you can specify exactly what resources you want Ray to be using, including GPU resources. And then in the case of parallelizing, creating a parallel task or a parallel function, you would just use this nice decorator syntax at ray.remote, and this is telling Ray that you'll process this function remotely. And then to actually go and use the function, you use dot remote and then pass in whatever arguments. So this is also going to happen in the background asynchronously across, in this case, 4 processes. And then to actually get the values from those processes, you would use ray.get on this list of what are called futures, so promises to return a computation to you. And a similar concept exists for Python classes. So you can make all of the methods of a class remote as well. So you can imagine how, using this type of abstraction, you can create really complex applications that are able to do things in parallel. And the syntax is pretty similar in terms of calling the dot remote method of your Ray object. One of the advantages that Ray might have over Dask, for example, is that Ray is able to actually use a shared memory store. So it can be a little more memory efficient, whereas Dask has basically a store for objects, which is per worker. So it's having to, in some cases, replicate objects and maybe use more memory than you would need to otherwise. So that's one potential advantage, especially if you have like a lot of large memory requirements for your application. And there are ways to run multi-node array. So the docs here have some great examples and also helper scripts that you can create SBatch scripts to set up array cluster. And everything about your application code should pretty much be the same. It's just how you actually get the array cluster started that's a little different. And there's a lot of other projects happening under Ray that are worth checking out. So including data sets, and that's where you find the Dask on Ray backend. And this includes support for basic distributed data transformations like map, filter, and repartition. There's RayTune, which is all about hyperparameter tuning for ML frameworks like PyTorch and TensorFlow. RLlib is about building scalable reinforcement learning. And then this workflows is I think, in alpha. So it's a more, very new project on Ray. But it adds some durability if you need some more production quality distributed applications. So I think we'll end there and then take some questions. And just to remind you, you can visit our office hours, take a look at our past trainings. We have a lot of great FAQs that we've curated over the years. So those are definitely a good resource to take a look at on our docs. And then if you're still having issues, you can always reach out to our ticketing system. So thanks a lot for listening, and we'd be happy to take some questions now in our last 4 minutes or so.
I think we'll also be putting the recording of this training up at that training link that James mentioned, so you'll be able to come back to it.